Let's look at Euler's method. Let's look at Euler's method a bit longer. So let's first justify a bit more mathematically why we built the Euler's method like that. So let's take a Taylor series of y around 0. Then we have that yt is equal to y at 0 plus the first derivative of y times t plus the second derivative of y times t squared over 2, where the second derivative is computed at xi, where xi is somewhere between 0 and t. That means that we can write that y at times t is equal to y naught, that here is our initial condition, plus t times y prime 0 that we replace by f computed at 0 y naught, plus the second derivative of y computed somewhere in xi. The term y second computed at xi is the error term. So once we drop it, we are making our exact statement about the Taylor series into a numerical statement about the Euler's method. And that's why in the previous video I was talking about the second order term of the error. It comes from dropping the Taylor series at the first order. So now we have a justification of why we can build the Euler's method. But we can also use the Taylor approximation around h to compute y0. So we are inverting y0 and yh in the previous formula. Now we have y computed at 0 is equal to y computed at h minus h times y prime computed at h. Y prime computed at h can be rewritten as f, where t is equal to h and y equals to yh. And then there's the second order term that we're not writing. So we replace this formula into y1 equals to y naught minus h times f computed at t equals to h and y equals to y naught. We can make this a general statement where we are computing yn with respect to equals to yn minus 1 minus h of f computed at yn with time equals to nh. While this is formally exact, we have a small problem in here in the sense that we are defining yn depending on yn. This means that yn is defined implicitly. The backward Euler method, that is really just using the Euler method but backward, is an implicit method for this reason. If you have the initial condition and you want to get to the next step is defined with respect to itself. You're still able to solve it in the sense it's an algebraic equation that we can just solve, but it's not as straightforward as the forward Euler method. So there is a category of methods that are called adaptive methods. The idea is that if you're taking your initial condition, you're taking the tangent solution and the exact solution, the error that you're making, as we discussed before, depends on h squared, but we know the coefficient in front of h squared. It's the error that you're making is bounded by the second derivative of y in the interval that you just considered. But the second derivative of y is equal to the derivative with respect to time of f computed at t and yt. So if you work things out, what you have is that your error is bounded by h squared multiplied by a maximum of derivatives of f. Derivative of f with respect to time plus f times derivative of f with respect to y. So if we know f, we actually know how big this term can become. And we have a control, an understanding of the mistake we're making, of the error we're making. So we can consider that we can change the step size depending on how bad that term is. For example, we know that if f is constant, then the Euler method is exact. If f changes very slowly, locally, we don't need to know the generally, but in the neighborhood of where we are, if f changes very slowly, then the two derivatives of f that bound our error are small. So even if we take big h being fairly big, so big step sizes, we're still going to have a relatively small error. On the other hand, if f changes very fast, either in time or in y, we have to take small step sizes because our bound of the error, the part we cannot control, is getting out of hand. So we need to control our part to make it very small. The idea of changing the step is the idea behind adaptive methods. We adapt the step size depending on the situation we have around us. If the situation is bad, we go very slowly. If the situation is really good, we don't care and we go fast.